So just a reminder from our topic 3 that an ideal gas has no intermolecular attraction between its particles, which means an ideal gas has zero potential energy. This means that the internal energy of a gas is only the random kinetic energy of the gas particles. If you'll remember, the average kinetic energy of an ideal gas is equal to 1/2 the mass of each particle, an individual particle, times the average speed squared. In the thermal physics unit, we also learned that it's also equal to 3/2 times Boltzmann's constant times the temperature of the gas in Kelvin. This is just a reminder that Boltzmann's constant here, K, is equal to the gas constant divided by Avogadro's number, which gives us the value 1.38 times 10 to the minus 23 joules per Kelvin. If we wanted to find the internal energy of a gas U, and that gas were made up of n number of particles, we could simply multiply the number of particles n times the average kinetic energy to get the total internal energy of our gas. We can substitute the 3/2 kT equation into this, and we see that the internal energy of our gas is 3/2 n the number of particles times Boltzmann's constant times the temperature in Kelvin. If we were to expand Boltzmann's constant to be the gas constant divided by Avogadro's number, we would get this equation. And since the number of particles divided by the number of particles in a mole is the number of moles you have, lowercase n, our equation simplifies to 3/2 number of moles n times the gas constant times the temperature in Kelvin. And since the gas law tells us pressure times volume is equal to the number of moles times the gas constant times the temperature, which matches what we have here, we can replace nRT with pressure times volume. So we could also find the internal energy of our gas by taking 3/2 times pressure times volume. This means that if we wanted to calculate a change in the internal energy of our gas, delta U, we could simply take 3/2 the number of moles times R times the change in